I have a PhD in cryptography from Boston University, and do a lot of cryptography stuff. Um, Sorry, the screen's popping up. But that's my background.
Thanks, Ethan. Um,
Hey, I'm Pritesh. I work with Amazon. I'm senior software engineer there. Also, I'm maintaining a Notary project.
Hey, this is Samir. Good to meet you, Ethan. I'm also an AWS employee, but I been working with the Notary project for a good 3 years now. Really excited for you to be here and see what you have to present for us. Looking forward to it.
and Ethan, I actually we met on Slack, but just to introduce myself. So I work for Microsoft. I've been doing container secure supply chain for more than 2 years at Microsoft. I've been actually dealing mostly with security and containers for since 2016. I don't know, 6, 7 years, 8 years already, and cloud computing, longer time. So I started with Azure, Microsoft Azure in 2009. Then I left Microsoft. I spent some time doing AWS and Microsoft and a little bit Google consulting for the cloud, and also spending like some time in the security side, as I said, since 2016. Not so much cryptography, but the rest of the security. David, I think do you know Ethan or
A little bit, a little bit.
a little bit? Okay. Do you want to introduce yourself or?
Yeah, I'm
Thank you, David.
David Dooling. I'm at Docker. Yeah, we worked with Ethan in adapting the open pub key solution towards signing.
Okay, I think we can get started. So if other folks join, Ethan, your stage.
All right, let me get this shared. That work? Just the sharing. All right, yeah. Can everyone see that?
Yes, I can.
All right, you can see my slides.
Yep.
Yes.
Yep.
Nice. So I updated these slides really recently because talking to Toddy, he sounded like he wanted more detail into the signing formats and how we handle different things. So there's a bunch of slides that drill down will drill down fairly far into um, our JWS and some of our certificate formats. Um, but let me get started. Who's here is familiar with the like Zuku's trilemma? Um, the basic idea is that it's one of these trilemmas where it's not it's not an unsolvable trilemma, but generally in a system you're forced to pick you're forced to pick two of three desired properties. So you can have like human readable names, which are decentralized and meaningful, but they're not secure. Anyone can say that their name is Alice, even if their name is not Alice. You can have meaningful and secure names. This is what the Web PKI essentially builds, where you trust a third party. Um, and so the names like google.com are meaningful, but they're not, and they're secure because there's a party that's issuing certificates, but they're not decentralized. And then you can have things which are decentralized and secure. For instance, Bitcoin, where the names aren't meaningful. Like if I tell you my name is just my public key, that's my identity. it's very secure, very decentralized. You don't need a certificate authority, but no one knows what, like, 0WI6ZX. It doesn't mean anything to people. So our sort of high level goal with Open PubKey is to bind meaningful names to public keys without asking users to do key management, because looking at the history of client certificates, humans are just very bad at certificate management, at managing secrets, managing signing keys. There's the famous story of the guy that has lost something like a couple $100 million in Bitcoin in a dump because he threw his hard drive away. So we want to get away from the problems of asking users to do key management, but we also don't want to introduce new trusted parties. We want to use the existing ones. In this case, OpenID Connect. So I'm going to jump a bit ahead. I'm sure everyone on this call knows what OpenID Connect is, but just super quick, one of the reasons we care about it is that almost all identity systems, at least for human identities, are now being built on OpenID Connect. So it's very likely that people have this already built into their workflow. Almost everyone has a Gmail account or a Microsoft account. So there's already someone that you're trusting for identity there. So the real short version of OpenID Connect, and this is the public flow. And feel free to interrupt and ask any questions. I realize this is fairly high level. So you have a user, Alice. Alice is going to want to Alice is a Gmail user, so Google is the party that should identify that Alice is alice@gmail.com. To do this, she authenticates to Google. Google issues an ID token. In many cases, the ID token actually goes to the audience, but in the public flow, the ID token goes to Alice, and now Alice can present this ID token to the audience, where the audience is the party that's trying to learn if Alice is who she says she is. And ID tokens are JSON web tokens, so JSON web signatures, and they contain information about the user's identity, like their email address, and then they also contain a list of signatures. With JWTs, this list is restricted to only one signature, but with JWSs, this can be more than one signature, and the signature is just Google's. Is just signed by Google. And so when Bob wants to check this ID token, he can download the OpenID provider, in this case Google's public keys, from this well-known URL that Google provides, and then can verify the signature. And this pattern is called bearer's authentication. Alice essentially gets an authentication secret, an ID token, and she presents this ID token to authenticate as Alice. She essentially reveals her authentication secret. To prevent Bob from to prevent different audiences, because you are revealing this ID token. For example, if I were to present, like, let's say Bob Corp learns Alice's ID token because Alice authenticates to him. How do we prevent Bob Corp from replaying this ID token to Carol Corp? Well, the ID tokens issued contain the audience that they're intended to use for, and Bob and Carol Corp will see that the audience is not correct, and will reject the token. Does that make sense? It's probably going over things people know fairly well already.
Yep.
So as mentioned, these are bearer tokens. What's the problem with bearer tokens? Well, they only authenticate the identity. They don't authenticate the messages. So if you have a malicious web server here, it can just it can just alter the message that's being sent. So rather than saying what Alice originally said, give Bob $5, this changes to give Eve $1,000. And the database only receives the message. The message has no signature on it. So the database just has to trust that it hasn't been interfered with as it proceeds to the back end. So the essential idea is give Alice a public key, and then Alice can use it to sign messages. With her ID token. So if the public key is associated with her ID token, each party here can check that the message is actually signed by the identity who is authenticated. And then the web server or any party on this path can't alter the messages, and the database can check that this was in fact signed by Alice. So we're going to look at one of the other approaches to binding identities to public keys, and I'm a really big fan of this approach. It's the Acme approach. Essentially, what you do is you create a certificate authority. Alice supplies the ID token and public key to the certificate authority. The certificate authority checks that this ID token is valid and then issues a certificate for that public key. Then Alice can sign messages and send the certificate along with the message. And audiences can look at the certificate and say, hey, this was signed by a CA I trust. The certificate says that this is alice@gmail.com's public key. Therefore, we can verify the message under this public key and then under Alice's identity. Unfortunately, though, this approach adds a second trusted party, the certificate authority. So so thinking about the various parties that could be compromised, if the OpenID provider, say Google, is compromised, then an attacker can get certificates issued from the certificate authority by forging ID tokens as Alice. So you have a point of compromise in terms of the OpenID provider. And then in addition to that, you have a point of compromise in the certificate authority, because if the certificate authority is compromised, then you can issue the attacker can issue certificates for anyone. So there's two single points of compromise in the system. It's Acme sort of added a second point of compromise. So we have Acme, which you can use today. It does add a trusted party, and it has two single points of compromise, but it's a fairly straightforward scheme to build out. There is a proposal, OpenID Connect Squared, which modifies the OpenID Connect protocol to add public keys into it. It does not add any trusted parties, but it can't be used today because it requires that OpenID Connect change. And it has one single point of compromise, the OpenID provider. And then there's OpenPubKey, which doesn't add any trusted parties and can be used today because it's compatible with the existing OpenID providers. But it still trusts, if you're authenticating alice@gmail.com, it still trusts that the OpenID provider, Google, isn't malicious. Google can still impersonate Gmail users. And then we have OpenPubKey plus the MFA cosigner. And this adds an additional party, which removes trust from the OP. And in this case, then there are no single points of compromise. So I'm going to go into a little bit how OpenPubKey works. This is the sort of high-level explanation. Is everyone with me so far? Awesome.
Yep.
So the most basic way to think about it is, remember before when Alice went to the OpenID provider, and authenticated. As part of this authentication, she supplies a nonce value that she generates herself. So what we're going to do is Alice is going to generate a key pair, and she's going to put her public key. She's going to set the nonce equal to her public key, and then send that to the OP. And then when she authenticates, she will get an ID token where the ID token contains her public key as the nonce. And this essentially transforms her ID token into something like a certificate, because it is binding her email, her identity, with her public key, signed by her OpenID provider. And the important thing here is that because the nonce is part of the payload, it is covered by the signature from the OpenID provider. So OpenPubKey has some additional details, which I'm going to look into. We're not just putting the public key in the nonce. We're being a little bit more sophisticated about it. What we actually put in the nonce is the hash of the public key, a random value, and the algorithm for the public key. The reason we put the random value in here is that the nonce is intended to be cryptographically random. It's a nonce, shouldn't repeat. So we want to randomize the nonce value, even if a public key was reused. In general use for OpenPubKey, we expect people just to be generating a new public key on every authentication to the OpenID provider. But if they were to present the same public key, maybe they want to use like a pass key or something, then the random value will ensure that it's random. The OP is cryptographically unable to even tell that this is not a random value, that it is in fact committing to other values. But this presents a bit of a problem for us, because if we just stuck the public key in the nonce, that's cool. You look at the ID token, you find the public key, you can start verifying signatures. But if it's the hash of the public key with some other values, the ID token alone is no longer sufficient to learn Alice's public key. If the person has Alice's public key and this random value and the algorithm, they could hash them together and check, but what if they don't? So we want to include the values that open the commitment to the public key and the nonce together with the ID token. And ID tokens are JSON web signatures. They're a JSON web tokens, which are a subtype of JSON web signatures. And this means that as JSON web signatures, they can accept additional signatures. So what we do is we take Alice takes the values that are hashed into the nonce, and she adds them as an additional signature on the ID token, which we now call the PK token. And she signs this with her signing key that matches the public key. So this ends up serving two purposes. Purpose one, everything's bundled together so that someone can verify signatures from Alice without having to search for anything. It's all just one JSON web cryptography object now. But in addition to that, it also serves as a proof that Alice knows the signing key. And this helps with rogue key attacks, which I can go into a little bit, but unless anyone really wants to talk about them, I won't go into. But this also serves as a proof of possession of the signing key. Does that make sense to everyone?
Yep.
Yes.
So I'm going to go into a little bit more detail on the so let's see, where is the So I'm going to go into a little bit more detail on the PK token and how signing works. So one of the problems that we sort of had to overcome in OpenPubKey is how do you actually handle JWSs with multiple signatures? Because there's very few people out there that are doing that. And like while the standard does support it and a lot of the libraries support it, as far as I'm aware, I wasn't able to find any projects that were like really dealing with this at scale. So added like two conventions. One convention is that if the first signer, the OP, chooses the payload. And then if we want to add additional data to the payload, like there's a second signer that has something they want to say, like for instance, this is Alice's pub key, or maybe some additional metadata about Alice. They encode the additional claims in the p header, and those are claims made by that signer. And then to deconflict the different signers and who generated what p header and what signature, we use the type field, TYP. This is already existing in JWTs. JWTs just have a type of JWT. But now for the client's claims, we use the type of CIC, and when we have even more signatures, which I'll look at some in a second, we just sort of extend and we specify a new type, which is like who handles that signature. And each signature signs their p header and the payload. So basically every signer is saying, these are my additional claims, and then here is the and I also agree with what's in the payload. Does that make sense to everyone? This is the first time I'm talking about this. This was something we added fairly recently. We used to just infer based on order, but this is much nicer and much more flexible system. So when we want to sign,
I have a question. Sorry,
sure.
won't you be decoding protected headers without verifying signature now? Basically, you would be trusting the payload and the protected headers without even knowing whether you should trust them or not.
What do
I'm
you?
thinking about, let's say,
Yeah.
if there's any JSON bug or JSON vulnerability you are passing, or you are reading p headers now without trusting them.
What do you? Can you give an example of what the attack would look like?
So, for example, there's a let's say there's a JSON vulnerability right now. I mean, JWT is by default JSON format, so I just cannot say it.
All
But
right.
for example, you would at least doesn't applies in JWS use case because JWS is by default a JSON format. So I was thinking something more on the line of, let's say if a parser has a vulnerability, now you are decoding the payload without even verifying the payload.
Verifying that the payload is signed.
Yes, it's intended and it's signed by same person, same identity, which you are trusting.
So you would still like the way you would verify a PK token, or the way that we verify PK tokens, is we take the first signature, we check that it's of the correct type, and then we follow standard JWT verification as if the token was the payload and that p header and signature, and then we do the next for the next p header and signature. So um, we're not trusting the p header until after we verify the signature. For the client claims, some of that verification includes checking that the public key in here actually matches the public key committed to in the nonce. But for the OP's signature, it is just your standard ID token verification where you take the p header, you look up the KID, you download the KID from the issuer that you've basically like hard coded in there, and then you verify the payload and p header are both signed correctly, and then you just do the essentially the same thing for the next p headers with additional validation for things like that the public key is hash 2 in the nonce. Does that make sense, or did I
Yeah,
something?
yeah, but makes sense. Yeah, it makes sense. Yeah.
So for some of the protocol stuff and authentication, we at least internally we try to use JWSs. So let me actually, where is the slides? Because unfortunately, all right. All right. So we have this extension of JSON web signatures called OSM, which is Open Pub Key Signed Message. And the way this works is you have a message that you want to sign. Let's say Alice wants to do the old Mark Twain quote, "All is discovered, flee at once." And so she puts this into our signing code along with her PK token and the signing key that is associated with that PK token. And this generates a JSON web signature where the key ID is equal to the PK token. And it's just signed by her. And then the nice thing is that she can send this with she can send her OSM with the PK token. People can check that it is actually for this PK token. So someone can't, manufacture a PK token which has the pub key or do some like weird tricks where they substitute in different PK tokens. The message commits to the PK token, and then you can, combined with the PK token, verify everything in the PK token, extract the user's public key, and then verify the signature on the payload. And the code for this looks like this. You essentially verify that the PK token is issued by who you want it to be issued by. So you're like, is this a valid PK token with the audience for Google? And then using the PK token, you just call verify signed message on the signed message, and it will tell you whether it is signed by the user in the PK token. So we can transform PK tokens into X509 certificates. And this is a pattern that we use a lot. I kind of dragged these were originally backup slides that I dragged out because I think you'd be interested in the format of this. So if you want to turn a PK token into an X509 client certificate, you can put the public key in the public key of the X509, and then you can encode the PK token in JWS format in the subject key ID. And then anyone looking at this, anyone that has this client certificate can just use it like a regular client certificate. Like if this is issued by a CA, they can just be like, oh, I trust that CA. Oh, here's the pub key. And like, oh, the client certificate signed this thing. But then if someone wants to have stronger security, they can pull the PK token out of the subject key ID and then check that the user's public key matches the public key in the X509 certificate, and then and also verify that the PK token was like issued by Google and that the user did like sign the P header, and they can open the commitment. And we do something very similar for SSH certificates. It's almost exactly the same approach. It's a very flexible approach. So we can take an SSH certificate. We set the user's public key to we set the SSH certificate's key to the user's public key in the PK token, and then we stuff the PK token into a SSH certificate. And this can be self-signed, or it can be issued by a CA. So I'm gonna move on from that. Does anyone have any questions?
Yep, I have one question, sorry. How does clients verify signatures? How do they get all the certificates to verify OpenID signature and
So
things like that?
so if you just put this in an X509, as long as the client trusted whoever issued the X509, they could use it as a regular X509. If they want the additional verification of verifying the PK token in the X509, then they need to use like the open pub key verification code. So for
So like for OpenID, as far as like, correct me if I'm wrong, I have lived in knowledge in that area, but servers rotate that key frequently. They don't maintain the old public keys there, old certificates there. Like for example, any OpenID server or provider doesn't maintain all the historical keys, so they maintain all the historical keys.
Yeah, so that's an excellent question. So for things like SSH and logging into servers and talking to web apps, it's totally fine to have the PK token no longer be valid when the OP's public key gets rotated out of the JWS repository. But for things like you want to verify the signature in 2 years from now, similar to what Docker's doing, there is this problem where if the key changes, you can't that breaks the verification path. And so there are a number of ways to solve this. One of the ways proposed is the Zachary Newman paper, where you use SigStore's transparency log to store OP public keys, and then you can go and check them. I believe Docker is exploring this with putting the public keys in Tough or in some other solutions. And then there's also like I wrote this up last night. So there's also just other sources where you can pull these public keys from. So Sui, this blockchain uses OpenID Connect to do to basically like move funds and do like smart contract management. So their entire consensus layer commits to the public keys of at the JWS URIs for I believe in production they have Facebook and Google's OIDC. They do have Twitch, but I think it hasn't been deployed yet. And I think their testnet has like eight different OpenID providers. And so I was pulling this in to OpenPubKey last night, and so you can just get a repository of the public keys from Sui. But yeah, there's yep.
Again, you would be trusting one more party for this, right? I'm assuming, like, I'm not sure how they're doing this, but let's say whoever is maintaining this, again, you are trusting that party to do the right thing.
So from a high level system point of view, you are now trusting that the Sui blockchain functions properly.
Yes.
They
have the right public key, which Google said it, or OIDC provider says it was there, and they have put the same public key there. Otherwise,
right. But it is multiple parties. Like they're doing this at the core consensus layer. So
okay.
The consensus of their blockchain depends on JWS repository state.
So basically, anyone can go and verify whether it's right or wrong, and based on that, you can
Yeah.
trust it. Okay.
So I believe every block producer, when a block comes out, checks that these keys have been properly attested to with the new block, or with the but you are now making a trust that this system functions properly, um, and I think short of changing OpenID Connect, you need some system that records this information, and then it becomes a question of how do you like audit this and
Yeah.
detect this behavior. So the Zachary Newman approach, where you're writing these public keys into Recor, I believe the way that it works is that you have auditors who look at Recor, and if they see a write that is bad, they alarm on it. And if you had something, I don't think Newman's approach has full CO signing the OP public keys. But if you did, then you would have this trusted, we would have this party that is trusted not to misbehave, but you have
Mhm.
like roughly 2 weeks to detect misbehavior, um, uh, which is a like fairly good
Yeah.
security. Um,
Thank you.
I mean, I think the ideal that I would like is that you can just that the
So put in the signature.
what?
Why can't you just keep the public keys in the signature itself when Alice or Bob signs it, this counter signature? Why not to just add them there? Because at that time they are already present. And I'm assuming the OpenIDC providers don't change root frequently.
Um,
So if you
so,
bake the signature as a protected headers or as unprotected also inside the second signatures,
so the
probably.
problem, if I understand your question, it's um, uh, get the OpenID provider's public key, package it with a signature,
Yeah.
that Bob has them. Um, so the problem with that is that the OP public keys are not signed by the OP, they're just available. So once they move off of the OIDC provider, Bob has no way of knowing whether that is actually Google's public key or not.
Oh, makes sense. It's just like lack of knowledge on OIDC providers. So they don't have a PKI, they just have a random keys and they maintain the keys. It's like, ignore that. Sorry, I need to read more on
Yeah, no,
OpenID providers.
it that is exactly it. They don't have a PKI for this. The idea is just you go to this URL and you download them. Something that I found very frustrating is that several OpenID providers will actually make their public keys available as X509 intermediate certs, but they're all self-signed. They're not like issued by
Ah,
Google CA or something. So it's like if they just sign them, then at least you
yeah,
the public key from Google, and then use certificate transparency, use the web PKI certificate transparency to then be like, oh well, here's Google's root key, and then here's and
yeah.
track it all down. But no one does that currently. The OIDC for VC draft, which is the verifiable credentials draft, um, argues that sort of proposes that they do this, which I think would be fantastic. I would love it if they did that. But currently they don't. And it is, I know of no way of pulling I know of no way of proving that like a TLS cert that a TLS session used a particular like public key, because you do download them over TLS, but because of the symmetric encryption that TLS uses, you can't like have like a proof of transcript with Google or something like that, which would also be awesome. But I think probably the future is that they will be like signed by the.
Yeah.
That's my I can't speak for the standards community, but like looking at it, it's like it's so close, and some of the standards are some of the proposed standards are like, hey, let's do that. It would be wonderful if that happened. And I
Yep.
think it will eventually. Um, so one of the issues is that maybe you're comfortable trusting Google to identify Gmail addresses. I trust them every time I use Google, sign into Gmail. But let's say you don't. I've definitely seen some hacker news threads where people complain where they're like, "Hey, I don't want to have to trust Google for anything. I'm not going to let Google, SSH into my box by like." Maliciously signing an ID token and doing all of this. We have a optional protocol that we can run in OpenID Connect, which removes the trust from the OpenID provider by doing independent authentication of the user. So the way this works is just as before, OpenID Connect runs. Then we have this third party, which is the MFA cosigner, that also has a JWix URI and public keys. And then Alice, after getting her ID token, can do an independent authentication to the MFA cosigner using, like, say, a YubiKey or the fingerprint reader on your MacBook. And then the cosigner issues a certificate. And this certificate, using the trick that we love so much with JWS allowing multiple signatures, it's just an additional signature on top of the PK token, making additional claims about the user. And unlike Acme, this second party doesn't add any trust. If the MFA cosigner is fully malicious, well, you're just back to the same state as you were if no MFA cosigner existed. It only subtracts trust. It does not require any trust itself. And it allows you to even maintain security against a malicious Google. Does that make sense to everybody? I think you're muted.
Yep.
Yeah.
Makes sense to me.
Yeah.
Pritesh.
Yep. That's neat. Yeah.
And when we think about X509 certs or certificate authorities like Fulcio, like they actually are in a really excellent position to be this cosigner. Because if the MFA cosigner not just issues the PK token, but also issues like an X509 certificate that encodes the PK token and then signs it, people that just want to trust the cosigner or the CA can do that, and keep their workflows that work today. But then if at some future point they wish to add additional authentication, they can always extract the PK token from the X509 cert, and then do this additional verification. So in some ways it can kind of act like an accountability mechanism to certificate authorities, without requiring that everyone switch to a new protocol. Those who do inspect this information can hold the CA to account. One area that we haven't built yet, but I'm really excited about, going back to the OP public key rotation problem, is that if the MFA cosigner signs the public keys in their JWix URI, in their JWS URI, then like at least one of the parties can sort of, how do I want to say this? the cosigner is essentially now attesting to the historical keys of the OP at that point. Because you would look at a payload, you would look at a PK token and be like, well, I don't know if the OP's public key is correct, but the cosigner's public key is signed, and therefore you could then trust purely the cosigner. But generally, when we think about it, we don't think about it that way. We think about the cosigner not adding any trust. But the sort of like longer term approach to OP pub key rotation, if you have a source like a TUF or like the SUI blockchain that you have made an assumption is functioning correctly, you can use the cosigner again as like a additional security mechanism on top of that. So it's like, oh well, if this fails, at least the cosigner can then tell me that it's failing. I don't know. Does that make sense? There's no slide on that. It's just something I've been thinking about. And given the questions so far, I wanted to add it.
Sorry, I lost you there at cosigner. Why do we need cosigner? A basic question here.
So we
Like I
don't.
agree that OP don't trust OIDC provider, but if they trust cosigner, why they need OIDC provider then, right?
So
So,
can you restate that?
okay, so I think from what I understand, just correct me if I'm wrong here. OP don't want to trust OpenID provider. That's why MFA cosigner came into the picture, right?
Right.
So if they trust MFA cosigner, why they even need OpenID provider?
So the idea here is that they trust neither. If the MFA cosigner is malicious, it can't forge PK tokens without conspiring with the OpenID provider. So if you add the MFA cosigner, then you now have two parties that must be compromised to compromise the security of your system. So it's like it's like it's like an or rather than an and.
Makes sense. Yeah, that's where I didn't understand. Like, it makes sense now because like instead of trusting one party, now you're trusting both the parties and you're verifying both the signatures.
Right. So it's like I always have this analogy in my head where people talk about like zero trust. And I know that zero trust is basically just shorthand for Beyond Corp. But I always think about like trust as a number between zero and like and infinity, where like if there's a single point of compromise, you have one trust. But if two things have to be compromised, you have 0.5 trust. Um, if you have 2 points of compromise, you have two trusts. And so you want to get the number as close to zero as possible. You basically like take the limit of zero as you add more parties that basically keep the other parties honest.
Got you.
And so sort of reiterating that point, we removed the OP as a single point of compromise, and we don't introduce a new single point of compromise when we add the MFA cosigner. So use cases, everyone's familiar with the Docker use case. Bastion Zero has built the SSH use case, and we're looking at other use cases. I think some of the really interesting use cases that we haven't fully explored yet is end-to-end encrypted messaging. Who here uses Signal? So like that is that annoying thing where you like someone's public key switches and then you're like, well, maybe I'll bring it up next time I meet them, and I've definitely done the dance where I check the public keys and everything, but it's like so hard to do. But with something like OpenID Connect, with something like OpenPubKey, you can just send the PK token. And sure, if the cosigner and Google are both compromised, then an attack might be possible. But today, an attack is just possible by like changing the public key. I know Signal kind of acts like a trusted party to make that a little bit harder, but it's like this would only like add security to Signal. It would add the number of parties that need to be compromised before security breaks. Um, Additionally, web authentication um, uh, is a really interesting one to me. And I'm just going to jump ahead to that. So you can run all of this in like a JavaScript client in a web browser, and then you can sign API requests to servers. So this is like really cool. And one thing that we've thought about is you could add like a plugin to like MySQL or Postgres. I don't know if Postgres has plugins. I'm more familiar with the plugin system of MySQL, or it's basically a C++ file that allows you to add additional authentication mechanisms to MySQL. So you could have the whole message all the way into the database be like signed and then run like a database procedure in the browser. The thing that's really cool about this is a while ago, browsers all added the Web Crypto API. How many people are familiar with the Web Crypto API? So it's the coolest thing. I love it. It's basically like an HSM built into your browser. Well, technically it's a SSM, it's a software secure module. But what it is that JavaScript can say, hey, generate me a key pair and make the signing key non-extractable, which means that the JavaScript, no matter how evil it is, cannot ever actually read the signing key. It can just ask the browser for signatures on the on that signing key. And it can bind that signing key to a particular origin. So only that JavaScript at that origin can get signatures under that public key. So this provides like really good security because now your JavaScript in the browser, even if it's totally compromised, can't steal the signing key. Unlike cookies, which are like transmitted on every request, right? Like putting your signing key in a cookie is like it transits the internet every time you make an HTTP request. Putting it in local storage is also pretty scary because local storage is fairly hard to protect from cross-site scripting. And then two, you will always, if you weren't using this, you would always be using JavaScript in the browser to do the signing, which is another point of compromise. So this provides significantly better security than like cookies, even HTTPS non-extractable cookies, and it lets you sign requests that can be like validated across like an entire service mesh. So this is something we haven't built yet, but I'm really excited about. I was super excited when it got added when this feature got added to the Web Crypto API. And I'm kind of surprised it isn't used more in web security. And I saw there was a message. I'm not sure when someone.
So Ethan, we are running out of time, but that's
Yeah.
actually great presentation. I had just a few questions I wanted to ask them before we end for today. Sure. And we'll be happy actually to have you again to talk about this stuff. I just wanted to ask questions about actually you like how do you remove trust from something, right? And take for example like OIDC. I don't want to trust everybody with Google account. Right? How do I, for example, configure my trust to say, okay, I trust only David and Ethan, and I don't trust, let's say, Pritesh, for example. Pritesh, no offense. But how is this configuration done? Because if I say, okay, that is signed by Google, right? That is too broader trust. Let's put it that way.
So let me just double check. So when you're thinking about this, are you thinking about the trust being that like David can get into your Google account if he has your ID token?
No, I'm thinking of so you sign something, right? You authenticate with Google, you get the OIDC token, right? And then you sign something. Okay.
Yep.
David also does the same thing, and Pritesh does the same thing. On my side, in the first scenario where I have the OIDC token only, not the kind of the additional keys added to the PK token.
Yep.
I cannot, so I need to list each individual email address and say I trust each only you and David, and I don't trust Pritesh. Right. So how do I restrict that? Because it becomes too cumbersome to go and say I don't trust everybody that gets OIDC token from Google. In general, I do not want to trust everybody that actually authenticated with Google. I want to trust just a certain amount of people.
So you're receiving a PK token from someone, and
Yes.
you don't trust that particular person.
Yes.
So I think that like you could just have a allow list of people that you trust. You get the PK token, you look at it, you extract the email address, you subtract the sub ID of the user that was issued for, and then you just reject messages from them. Since you have
okay. That means I need to actually keep a list of email addresses that I trust, right? That's kind of the way I restrict.
This is something we're using Tough for. So to define the policy of who you trust for what.
And in this particular case, the identity is the Gmail. Like if you take like Alice in this particular case, so let's say I trust Alice, right? So we see this PK token. If I receive email from pritesh@gmail.com, I can check my list, see that Pritesh is not there. I don't trust Pritesh. That's perfectly fine. Now, imagine that Alice's email gets compromised for a certain amount of time, right? You have between January 1st and January 31st, it's known that she went and signed a bunch of stuff that should not be trusted because actually I was a malicious person. I hacked her account and I started signing stuff. How can I invalidate only this particular set of signatures?
That's an awesome question. I don't have any slides on this. The way that I've been thinking about it is it's fairly hard to do with archival signatures from a long time ago using only OpenID Connect. Because the OpenID Connect revocation mechanism is based on using the refresh token to get new ID tokens. And when it is like, oh, I don't trust this authentication that happened anymore, it just it invalidates your refresh token. You can't get new ID tokens. ID tokens expire 1 to 2 hours, and then you're locked out. But with signatures, this is a harder problem. So we have a refresh flow with the MFA cosigner. Where the user can continually refresh, and the MFA cosigner can also do that same revocation of the refresh. However, imagine in your scenario, the signature was generated before the MFA cosigner recognized that the account was compromised.
Exactly.
And so in this case, it's a totally valid signature. The way that I've been thinking about it is either you have Alice have the ability to like sign things and like post them on a transparency log that are like, these signatures are malicious, please discount them. That has a bunch of issues with like non-reputability. It could just be Alice like faked the signature, like at some point you're
exactly
the signature. The other approach is that is to add an additional API to the MFA cosigner where Alice can say like I'm sort of like rejecting this period. But and like, these PK tokens are malicious and you should not trust them. But
Mhm.
again, it runs into the sort of core problem with non-repudiation of signatures,
Yeah.
everything you want. So I think that like you can do that, you can build these mechanisms in, and the cosigner provides a really nice place to build them in. But at the end of the day, the problem that you run into is that it's a policy decision. Do you allow Alice to say that her old signatures are not valid? Do you have some sort of signature revocation place that stores that and you trust that for that purpose? But it's beyond the like, don't trust this PK token anymore, like after this fact. Um, that's very doable, but when you start going backwards, you essentially run into a contradiction with what you want the signature for, and it probably should be solved out of band outside of Open PubKey. The sort
Okay.
of revocation of
Yeah,
signature.
I will be interested, like, to chat maybe offline with you about different options. I also have one more thing, but I don't want to go too much over time. Is we also are looking for disconnected scenarios, which means that, for example, how do you verify these things without, let's say, transparency logs, without any access to APIs and so on. That is also one thing that is important, at least for our scenarios. But yeah, thank you very much for the time. It was actually great presentation, and I think it's helpful for the rest of the folks. And I'll be happy to have you again here to talk more about this. So you're a good presenter.
Oh, thank you, and thanks for having me on. It was super fun. Loved all the questions. I do have an answer to your offline validation, but I want to be considerate of anyone's time, so I'm happy to answer that like offline, or if you want to stay on the call for 2 minutes, or we can just do it over Slack.
I can stay on the call for another 2 minutes.
All right. So the short answer is that one of the verification mechanisms that I haven't talked about in this is that parties can just keep their own, a verifier can just keep their own log of OP public keys. You can have some sort of like one-way diode where you're just pulling, every day Google's pub keys, and you just keep them in some, air gap database or something. Just you just use a one-way diode for. And then when you want to verify, you just check against that list. So as long as you're willing to run something like that, you can have pretty nice offline verification. But in a lot of the scenarios we think about, like, we kind of just want like someone to be able to hit an API and look the key up. But if you're willing to store that database yourself, you can get like really nice performance, and Google could disappear tomorrow in the cloud of smoke, and you would still have all the public keys.
Yeah, that is one of the things that we've been thinking. One of the problem that we see, because like synchronizing, let's say the public keys, that's fine. But when you have additional systems, like for example, Recore or any other transparency log, right? So you need to build all this infrastructure in multiple places and figure out how to get all the data from one place to another, which makes it a little bit more complicated. But yeah, the diode approach that you mentioned, that is what we are also eventually exploring, and also how you can feed this information frequently enough in order to, when something, for example, gets invalidated, or that something is compromised, this information can trickle down to all the consumers of it.
Right. So
okay,
I'll let you go. I'm super curious now that I hear you've been looking at this. But I'll
thank
ask
you very much again. Yeah,
thanks so much.
Really appreciate it. So I'll ping you on Slack, and we can continue there. Have a nice day.